Look up at the night sky. Every star you see is part of a much larger structure, the universe. But what you might not know is that this universe is in constant motion. It's not static, nor is it unchanging. The universe is expanding, and this expansion is one of the most intriguing and revolutionary discoveries in modern science. But why? How do we know this? And what does this expansion mean for the future of everything that exists? Welcome to Futuristic Findings. My name is Robert, and in this video, I'll show you why the universe is expanding. Our journey begins in the early 20th century, a time when the cosmos was conceived as an eternal and unchanging entity. The prevailing ideas championed by figures like Albert Einstein suggested a static universe existing in a state of perpetual balance. This view was challenged by groundbreaking observations that would begin to transform our understanding of the universe. It all started with Vesto Slipher, an astronomer who, while analyzing the spectra of distant galaxies, made a crucial discovery. Many of these celestial bodies showed a redshift in the light they emitted. This phenomenon, known as redshift, was not just a peculiarity in the data, but rather an indication of motion, a velocity suggesting separation. Slipher found that galaxies appeared to be moving away from us, but he lacked the ability to explain the nature of this motion or its implications for our understanding of the universe. The confirmation and expansion of this discovery came with Edwin Hubble, whose systematic observations allowed him to establish a pattern. He found an intriguing relationship. The farther a galaxy was from Earth, the faster it was moving away from us. This phenomenon was mathematically described in the famous Hubble's law, which demonstrates that the recession velocity of a galaxy is proportional to its distance from our galaxy. Hubble's law provided clear and compelling evidence that the universe was expanding. But what exactly is expanding, and why does it matter? The answer to these questions transcends the mere observation of an astronomical phenomenon. It requires rethinking the very concept of space and time. What is expanding is not the galaxies themselves, but the fabric of space-time. This expansion is not like an explosion from a specific point in space, but rather the stretching of space itself between celestial bodies. This understanding led scientists to formulate new theories about the origin and evolution of the cosmos, culminating in the Big Bang Theory. This theory proposes that the universe began in a state of high density and temperature and started expanding from that point. This expansion not only transformed our view of the universe as a whole, but also revealed a dynamic cosmos, constantly changing and challenging the notion of an eternal and unchanging universe. To understand the expansion, we need to go back in time to the moment everything began, the Big Bang. About 13.8 billion years ago, the universe was condensed into an incredibly dense and hot point. Then it started to expand. Imagine a state where all matter, energy, space, and time were concentrated in a single point, called a singularity. At this moment, the laws of physics as we know them were not enough to describe the conditions. This point was so dense that gravity and other fundamental forces became incredibly intense, and the temperature reached unimaginable values, exceeding billions of degrees. This early phase of the universe was marked by immense energy and infinite density, where subatomic particles and radiation coexisted in a state of high agitation. When the Big Bang occurred, it wasn't an explosion in a specific point in space, as is often imagined. Instead, it was an expansion of space-time itself. This expansion caused matter and energy to spread throughout the cosmos, marking the beginning of what we now understand as the expanding universe. Space did not expand from a central point. It grew uniformly, carrying galaxies, stars, and all cosmic content with it. This expansion was not like a typical explosion. There was no center from which everything moved away. Rather, it was the space itself growing and carrying all matter and energy with it. Imagine a balloon being inflated. The galaxies would be like points on the surface of the balloon. As the balloon expands, each point moves away from all the others, but there is no central point on the surface where the expansion starts. Similarly, the universe expands uniformly, with all galaxies moving away from each other without a specific point of origin. Now, we know that not only is the universe expanding, but that this expansion is accelerating. This phenomenon is attributed to something mysterious called dark energy. Dark energy is a mysterious component that makes up about 68% of the universe's total energy content. It acts like an anti-gravitational force, exerting negative pressure that drives space to expand at accelerated rates. Unlike matter and radiation, which tend to slow the expansion due to gravity, dark energy becomes more dominant as the universe expands, since its density remains nearly constant while the density of matter and radiation decreases over time. Although its exact nature remains unknown, dark energy is often associated with the cosmological constant, introduced by Einstein in his theory of general relativity. Originally, Einstein proposed the constant to balance gravity and maintain a static universe. But after the discovery of the expansion, it was reinterpreted as a manifestation of this mysterious expansive force. The impact of dark energy is not just theoretical, it dictates the fate of the universe. If the expansion continues to accelerate, the future of the universe could be quite dramatic. One possibility is the Big Freeze, in which galaxies will become so distant that the universe will become cold and dark. The Big Freeze is the most widely accepted scenario among cosmologists and is directly related to the influence of dark energy. As the universe's expansion accelerates, galaxies will continue moving away from one another at increasing speeds. Over billions of years, the gravitational interactions between galaxies will weaken, leaving each isolated in vast voids of space. Eventually, the stars within these galaxies will consume all available fuel, becoming white dwarfs, neutron stars, or black holes. The temperature of the universe will plummet drastically, approaching absolute zero, creating a dark and barren cosmos where thermodynamic activity essentially ceases. Another possibility, although less likely based on what we know today, is the Big Crunch, in which the expansion reverses and everything collapses back into a single point. The Big Crunch is an alternative scenario that depends on gravity overcoming the expansive force of dark energy, something that seems unlikely based on current data. In this model, the universe's expansion would slow down until it stops, reversing into a gravitational collapse. In this process, galaxies would move closer together, temperatures and densities would rise, and the universe would return to an extremely dense and hot state, similar to the singularity of the Big Bang. Some theorists suggest that in this case, the Big Crunch could trigger a new cosmic cycle, leading to another Big Bang, a concept known as the cyclic model of the universe. These possibilities illustrate how our current understanding of the universe is both fascinating and limited. While evidence favors the Big Freeze, futuristic findings may reveal new forces or dynamics that could change our view of the cosmic fate. I invite you to join us in uncovering the secrets of the universe. See you on the next journey.